So I'll discuss the last one first. Okay. This was the problem. I mean, from the schematic, it's pretty obvious that it's symmetrical at the same excitation to either side. So it is like the common mode picture. Even if you don't recognize that, you can easily calculate the answer, even if you think of it as an independent circuit. So if we do use symmetry, this voltage has to be equal to this, okay, and that's all that's there to it. Essentially what we will have, the equivalent circuit will be this node connected to this node, okay. So we'll have R by 2, something like this. Now you also see that there is no current flowing into the gate at DC, and if this was some W by L in the equivalent circuit, it's twice that one. Anyway, that's not the concern as far as the problem is concerned. The problem in question asks you, the only thing it asks you is the current through the resistor and current through the MOSFET, okay. So if a certain current I1 is flowing here, this will be 2 times I1, okay. So clearly no current flows into the gate, and I1 is I bias, and the current through the resistance is 0. I think most of you have got this, so this is fine. Any questions on this? So it's pretty simple. Once you recognize the symmetry, it's very simple. Even if otherwise you assume different voltages here and write Kirchhoff's current law everywhere, you will get the same answer, obviously. Okay. The next one is when an antisymmetric input is applied. Okay. So this is clearly the case where you use the differential equivalent circuit. Okay. Now ID is given to be small, so you use the small signal equivalent. I think I asked you to only use GM to model the transistors and ignore GDS. Okay. So first of all, if I draw it in terms of the incremental quantities, it will be ID by 2 and ID by 2 in the opposite direction. Okay. Now, because it's symmetrical and it's driven antisymmetrically, the line of symmetry is at 0 volts incrementally. Okay. This is VG, this is GM times VG, and the same thing goes here. This is at 0 volts because of symmetry. Okay. So obviously these two current sources go away. Okay. And you have ID by 2 flowing through a resistance R. So this voltage is ID by 2 times R, and this will be minus ID by 2 times R. Okay. Again, pretty simple. Or you can straight away write down the differential equivalent circuits and move on. Okay. The differential equivalent circuit for this will be just this, okay, where the MOSFET is to be replaced by its small signal equivalent and the gate is at ground. Okay. This is fine. Everyone got this? In the third case, the excitation applied is in common mode, not differential. Okay. In this case, you connect the corresponding nodes together, form the common mode equivalent circuit and find the answer. So the common mode equivalent circuit will be just the incremental circuit is 2 ICM flowing driven into a transistor. What is the transconductance of this transistor? 2 times GM, because you connect corresponding nodes together, right? And this is R by 2. Okay. So if this is VG, the current source is 2 GM times VG. So this is what I get if I connect these two nodes together, this one and this one, in the incremental circuit. So again, the current through R is 0, R by 2 is 0. So I have 2 ICM equals 2 GM times VG, and this voltage, which is V1 and V2, okay, that equals VG because no current flows through the resistor. So V1 and V2 are the common mode current divided by the transconductance of the transistor. In the differential case, we had V1 and minus V2 to be equal to ID by 2 times R. So I think all of you have got this. What is the significance of this? What does it mean? So firstly, the common mode impedance is V1 or V2 divided by the common mode current, okay, which is 1 by GM, and the differential impedance is V1 minus V2 by ID, and what is that? 2R, R, right? So the differential impedance is R. I mean, the way it is defined, because you have, is this correct? Yeah, maybe I should define it to be divided by ID by 2. So it is 2R. Okay, each side is exciting ID by 2. So I will define the differential impedance to be the differential voltage divided by the current that is forced into the circuit. So it is 2 times R. So the differential impedance is different from the common mode impedance. Okay. So this concept we will see repeatedly in discussions of differential circuits. This will turn out to be very useful to bias the common mode in some way. So you can see that the common mode impedance is much lower than the differential impedance. Okay. So let's say you want to get differential gain. Then you have a differential transconductor pumping current into a differential high impedance. Something like this. Whereas to get common mode stability, the common mode to be biased correctly, you should have low common mode impedance. So we will come across a class of circuits called common mode feedback circuits, whose job is to achieve this goal, okay, to have a common mode impedance that is much smaller than the differential impedance. We will have different forms of this, but this is one kind of common mode feedback circuit. Okay. So you can clearly see the common mode rejection here, right? If you excite the circuit differentially, you will get large swing at V1 and V2. And if you excite the circuit in common mode, you get a small swing. That's the idea behind getting common mode rejection. Okay. Any questions on this? Oh, okay. That's a good question. Here, why did I say the input is ID by 2? So this is current, right? So when I think of current flowing into a port, this is the current that is flowing in, and the same current flows out. Okay. It's not this minus that, that's the input. Okay. It's the current that is forced into the one port. Whereas in case of a voltage, I apply a voltage across these two. So whatever voltage is here and this, I have to subtract one from the other to get the input voltage. So here also, while calculating the output voltage, I will take the difference between these two. And in this case, when I want to calculate the input current, I will just take either what is going in here or what is coming out of here. Okay. That's all. Any questions on the third problem? So we can go to the first one, which was to calculate the frequency response of this type of a circuit. So this is at some V bias Actually, the first part of the circuit asks you to calculate the swing limits, right? You can think of this as a transconductor and it's terminated in some voltage source. So what's the maximum and minimum values of V out? Why are there maximum and minimum limits? What happens if V out is too low? M2 will go into triode region. If it's too low, this will go into triode region. If it's too high, M4 will go into triode region. Okay. So V out has to be more than the saturation voltage of M2. Okay. And it should be less than some value which will keep the saturation voltage across M4, which is VDD minus VD sat 4. Okay. And we can calculate this quite easily also. What is VD sat 2? It's nothing but V bias minus VT2 or VT1. Okay. And what is VD sat 4? What is VD sat 4 in terms of VD sat 2? Yeah, I would rather not express in terms of small signal quantities because this is a large signal, although the answer is correct. That's what you get. The same current is flowing through M1 and M3, right, as through M2 and M4 also. So, this current is the same as so from this you can calculate what it is. VD sat 4, which is the same as VD sat 3, is so the two limits are derived like this. Okay. You want to keep the upper transistor and the lower transistor in saturation region. So this is the limit you will get. Incidentally, this is typically the maximum swing you will get in a CMOS stage, okay, because you will have some transistor on the upper side and some transistor on the lower side. So if you bring the voltage too low, the lower transistor will go into triode region. If you bring the voltage too high, if you make the output voltage too high, it could be by connecting a voltage source, or it could be by having an impedance, and the current that is flowing through it will make the voltage very high. Whatever it is, this voltage cannot go higher than VDD minus VD sat of the upper transistor. Okay. So the peak to peak swing that you will get will be the supply voltage you have minus twice the saturation voltage. Okay, or at least minus the sum of two saturation voltages. That is typically the absolute maximum swing you will have. Okay. So as you can see, as the supply voltage reduces, the swing that you have also reduces. Okay. So the next part was to calculate the frequency response. That is, the output signal is defined to be this I out. Okay. And you want to calculate the frequency response I out by VD. So what are all the parasitic capacitances that come into picture? Huh? So we have parasitic capacitances everywhere. We can write it down and see. In the incremental circuit, this is VD by 2. And this is, maybe I said CG as N, right? CMN. This is the drain bulk capacitance of the NMOS, and here we have the drain bulk capacitance of the PMOS, and the gate source capacitance of the PMOS. Okay, the gate and drain are connected together. So the transconductance will contribute an impedance of GMP, 1 over GMP. And we also have CGSP here of the fourth transistor, M4. Okay. And this is GMP. We have CDBP. CDBN, and a voltage source derived from the other side, minus VD by 2, and this is CGSN. Okay. So this entire thing is one transistor, this is the other transistor, this is the third one, and this is the fourth one. Huh? Yeah, the output is terminated in a short circuit. And the current I am interested in is this. Okay. So which are all the capacitances I can neglect right away? First of all, this and this appear across the output short circuit. Okay. And this this one and this one appear across the output short circuit, and this appears across the input voltage source. And this appears across the input voltage source also. So there really is only one significant node in the whole circuit, and for this control source, for this one, the controlling terminal and the control source are the same, they have the same terminals. So this can be replaced by a resistance 1 over GMP. Okay. So what is the current flowing through this? This one? It is GMN times VD by 2. if I write it in terms of frequency, Gmn Vd of S by 2. And what is the voltage at this point? So it's a parallel combination of this resistance and these 4 capacitances. Okay. We have the conductance plus the sum of all capacitances. So that is the voltage here. Sorry, minus of this. That's the voltage here. Okay. So it's a common source amplifier from this node to this node, and this is the transconductance, this is the load impedance, load admittance. Okay. So what is the current flowing through this transistor? It's GMP times this voltage in the upward direction, or GMP times minus of this in the downward direction. Okay, and it flows directly into the short circuit because it's terminated by a short circuit. That is one part of I out. What is the other part of I out? It's through this. Okay, because this minus Vd by 2 times Gmn, it gives you Gmn times Vd by 2 in the upward direction. Okay. That is the output current. So one part of the current goes through some frequency response which has a low pass response. Okay. So the path, this path has a low pass response. Obviously when at a frequency where these capacitances dominate, this voltage, this node voltage becomes almost 0. Okay. At very low frequencies you will have the current through this GM mirrored by the upper current mirror. Okay, and driven to the output. But at very high frequencies, the contribution will be 0 because the current mirror is not mirroring anything. So, what should happen at DC? You will have some gain, which is the sum of this GMN and this GMN. Okay, and at very high frequencies, this part will go away and you will have only this. So, you should have half the gain at high frequencies. Okay, so you do expect a frequency response of this sort. At low frequencies it will have some gain, and at high frequencies it will have half the gain. Okay. So if this is GM0, at high frequencies it will be GM0 by 2. And it's a first order response, so you will have one pole and one zero. Okay. So we will get a 0 on the pole, and 0 will be at twice the frequency of the pole. Okay. Sorry, I don't mean P2. This is Z1 is 2 times P1. Okay. Is this clear? So there are two paths to the output. Whenever you have multiple paths, you can expect zeros. In this case, one of the paths has no high frequency attenuation. The other path is a low pass filter. So at low frequency you get some gain, and at high frequencies you will get half the gain. Okay, only from one side. This is a characteristic of this differential to single-ended converter that we have. Okay, we have a differential pair, and then on top of it we have a current mirror, and we take the output only from one side. So, in all those cases you will have this type of frequency response. At low frequencies you will have something, and at high frequencies you will have half of that, which corresponds to having a 0 and a pole in the frequency response. Okay. Again, I think most of you have got this. Some of you have not counted the CGS properly and omitted this too. Okay. But otherwise, I think many of you, or at least most of you, have got the answers. Any questions on this, on analysis, or what the answer comes out to be? Now, coming to the second problem, that was about noise. So, again I had asked you to model the transistors only using GMs and ignore everything else. Okay. If I draw the small signal equivalent circuit, I will have GMP, and I will show all of the capacitances lumped into one. This is CdVn plus CdVp plus 2 times CGSP. Okay. And this is also the controlling node for the other transconductor, GMP. The output is terminated in a short circuit, and this is the current I am interested in. Now, also when doing noise analysis, I set the input to 0. Okay. So, when I set the input to 0, I have nothing on this side. Okay. And similarly, nothing on this side. These current sources are disabled. Okay. Now, we model the noise using a current source from drain to source. So, let us say this is IN1, this is IN2, sorry, I think according to the notation this is IN3, this is IN2 and IN4. Okay. This is the method for noise analysis in general. You model the noise of every transistor in the circuit and look at the output current because of each noise current, and you add them all up. Of course, the noise current itself is not of interest, its spectral density is. Now, you are considering noise from different devices which are all uncorrelated, so you add up the spectral densities. So, what is I out because of IN1? What is the contribution to the output noise from M1? What is it at DC? Huh? So, IN1 goes through an impedance of GMP, which gives you minus IN1 by GMP here, which causes a current to flow in this direction. Okay. So, at DC this is IN1. What about IN3? What about this source? Huh? Same. What about this? IN2. So, it is minus IN2. Okay. You should keep track of signs, especially because sometimes you can have it through two different paths and some part will cancel the other or something. Okay. If you, of course, after you calculate the whole thing, you can omit the signs when you are calculating the spectral density. And what about IN4? It's again minus IN4. Okay. So, the noise output is IN1 minus IN2 plus IN3 minus IN4. So, all of them contribute directly to the output. There is no coefficient multiplying any of those noise currents. What is the spectral density? It's the sum of all the spectral densities. Okay. IN1 is GMN plus GMN plus GMP plus GMP. Okay. This is the spectral density of the output noise current. You have the noise from two lower transistors and two upper transistors. So you get 16 by 3 kT GMN plus GMP. Okay. Now you can also calculate it for AC. This IN1 and IN2 will go through a low pass filter. Okay. And IN3 and IN4 will flow directly to the output. This is okay? What you will get is, in that case, this is the output current as a function of frequency. So at DC it has to be equal to the previous one, and it is. And what is the spectral density? What is the spectral density as a function of frequency f? So for these two we get 8/3 kT GMN plus GMP divided by 1 plus CP square is a shorthand, CP is a shorthand for this entire parasitic capacitance, plus (8/3 kT GMN plus GMP). Okay. And what is the input referred noise? Here by input, the input is Vd. Okay. What is the input referred noise? How do you find it? You are divided by the transfer function I out by Vd. Okay. So if you do it for DC, what do you get? What is the DC transfer function of the circuit? Huh? GMN. Okay. So at DC we get 16 by 3 kT GMN plus GMP divided by the square of the transfer function. Okay. You get 16 by 3 kT by GM, 1 plus GMP by GMN. So this again is a very typical result. If you have a differential pair, what we have is not exactly a differential pair, it's two separate common source amplifiers, but you try to realize the transconductance GMN. Okay. Here it is GMN. Because of that, you get 16/3 kT by GMN. That you always get. Okay. So just because you have a transconductance of GMN, you are getting transconductance GMN by the lower transistors, and because of those transistors, you are also getting a noise 16 by 3 kT by GMN. Okay. So in general, whenever you make a transconductance of GM, you can expect an input referred noise source of the order of 4 kT GMN. Okay. If you make it with MOSFETs, it will not be 4, it will be 16 by 3. Okay. This factor is not very important. It will be proportional to kT times GMN. So just because you make the transconductor, you can expect this much. This is like something as fundamental as having a resistor. Whenever you have a resistor, you have a certain amount of noise. Okay. Similarly, whenever you have a transconductance, you will have a certain amount of input referred noise. Is it okay? When I have a conductance G, I have a series voltage, okay, whose spectral density is 4 kT by G, isn't it? Similarly, when I have a transconductance G, I will have an input referred noise whose spectral density is of the order of 4 kT by G. So, it will be some factor gamma, let us say, times 4 kT by G. This gamma is dependent on how you make the transconductor. If you make it with bipolar, it may be half. If you make it with transconductance, it may be, if you make it with CMOS transistors, it may be 2/3. So, things like that, okay. But if you make a transconductance, you will have this much noise. Just like if you try to realize a conductance, you will have a certain amount of noise. You will have more than this, but you will have at least this much. So, this you have to take into account when you are doing analysis at the fundamental level. So, let us say you have not yet designed the circuit and you just decide that, oh, I will have an amplifier here, I will have a transconductance here, etc., etc. So, and you can't just assume zero noise for all those voltage controlled current sources, okay. If you are making a voltage controlled current source, you will have a certain amount of noise. So, that you have to factor in. This is okay? Next, this is dependent on implementation. So, typically you will get this much also because you will have something on top of the NMOS transconductors. Okay, we will see this again in our examples as well. We will have 1 plus GMP by GMN. Okay. And if you want to absolutely minimize the noise, you have to minimize the value of GMP. Is it okay? This is the noise contributed by the active load. Okay. If you want to reduce its relative contribution, you have to make the transconductance of the active load less than the input transconductance. Okay. And you can also calculate it for high frequencies. You simply divide this by the high frequency transfer function. So, I think some of you have done it only for DC, many of you have done it for the AC case, but what some of you have done is to calculate the current noise output at DC, but divided by the overall transconductance, overall trans admittance as a function of frequency. Okay, that is something inconsistent. I have not taken off any marks for it, but that's clearly not correct, right? You either do it at DC and say that my answer is valid for DC, or you do it for all frequencies. You can't take the current output at DC and divide it by the transfer function over all frequencies and say that's the spectral density over frequency. Okay. So, this is the noise contributed by the active load. Now, again, what the circuit that was in the quiz was different from the differential pair we were discussing, but it is similar in many ways. Okay. Why did we put the active load in the differential pair? To increase the gain. So, we wanted to put a high impedance. We wanted to have a high impedance. We had this circuit. And from this we went to okay. So, this was giving a much larger impedance than this. Okay. That's why we put that transistor M4 there, and then of course biased it appropriately. So let's say we terminate this in an incremental short circuit. What is the output noise current because of M4? If this is the output current, what is the noise current because of M4? Huh? What is it? Yeah, it just directly comes out. So the noise spectral density because of M4 is 8/3 kT GM. What is the impedance contributed by M4? GDSP, let's say. Okay. Now in this case, what is it? In this case, let's say I terminate this in an incremental short circuit. What is the noise contributed by R? This R? 4 kT by R. Okay. Or 4 kT times the conductance. And what is the output conductance? That also G. Okay. Now we put this transistor M4 so that we get a much higher output resistance or much lower output conductance. Okay. But that same doesn't hold for noise. It gives you a much lower output conductance, but noise is in fact more than this one. Okay. I have this backwards, right? The impedance contributed by the active load is much higher. So the conductance contributed by the active load is much lower than that of the resistor. But its noise is not proportional to that impedance. Okay, I mean that conductance. It is proportional to something else. Here, if you have a conductance G, the noise is proportional to G. But in an active load, you get a certain conductance. The noise is proportional to the GM of that transistor, not GDS. Okay, so you get much higher noise. So you can realize very high small signal impedances using a transistor in active region, I mean in the saturation region, but the noise will be much higher than if you used a physical resistor of the same value. Is this idea clear? So the noise of this is much more than this, although the conductance is much lower. The input referred noise is what we wrote here. Okay. So if you have a certain transconductance like this, you will have this much input referred noise. Okay, it's not dependent on the voltage gain, right? We are looking at just the transconductance now. So this is one disadvantage of the active load. If you had used resistive loads of the same value or even smaller value, you would have got lower noise. Any questions on this? This is a disadvantage of active load. I mean, we use active loads to, let's say we try to make every resistance using active loads. You will have much more noise than if you use physical resistances. Right. Huh? Oh, okay. One thing I have to mention here is this is specific to the way we made the active load. If you make it in a different way, you can potentially get higher. But the only way is to reduce the GM of the transistor. Okay. If you pass a certain current I through a resistor, okay, the voltage drop across this is IR, right? Now let's say you have a MOSFET to carry the same current I. What is the minimum drop that is possible across this? VD sat. Okay. Which we make to be much smaller than IR. That's how we get the active load. Okay. We can get the very small slope in the IV characteristic, but you don't have to operate here. You operate it somewhere here by using the nonlinearity. Okay. You get the slope of this curve, but the operating point at a low voltage. This is I versus V. Okay. That's why we use the active load. But what is the noise of this? If the voltage drop across this is some V naught, the noise current of this is 4 kT by R, which is 4 kT times I by V naught. I is, we can think of I as a given variable here. That is, I is the current we want to carry through this impedance. I is the DC we have to carry through this impedance. Okay. In case of a resistance, you need to expand the voltage drop across it, which is proportional to I. And what is the noise current of this? It's 8/3 kT GM. And what is GM in terms of I? 2I by VD sat. That's the most convenient form to use here. 8/3 kT 2I by VD sat. Okay. Which is 16/3 kT I by VD sat. Now here we have 4, here we have 16/3. That is a small difference in constants that we will ignore. But see, what happened was, using the active load we could cheat a little bit. That is, we didn't have to have a large voltage drop across it to get a high impedance. But we can't cheat in every aspect of it. The noise is still dependent on the current you have going through the MOSFET divided by the voltage drop that you can have across the MOSFET. Okay. So the noise is much higher, but we somehow get a small signal slope that is much lower. Although we cheated and got equivalently a much higher impedance, the noise is not related to that high impedance. Okay, it is still related to how much voltage drop you have across the device and how much current you have going through the device. Okay, this again you will find to be true. If you want low noise, you will end up having to bias everything at a high VD sat. Okay, which will compromise headroom. So just now I pointed out that the swing is VDD minus. So the swing limit in the problem was this, and this is the best case where you have only one transistor on top from the output node to the supply. Okay, there is only one transistor here and another on the bottom where you have just one transistor from the output node to ground. This is the absolute best case. You can imagine, without going through details, that if you have more transistors, it will add up to more voltage, which is taken away from the swing limit. So if you try to maximize the swing limit, you will minimize these, which will increase the amount of noise. Okay. Is this clear? Yeah, it will also increase. Okay, because it's a much higher current going into a high impedance, right? So the output current is okay, and its spectral density was, this is the output current into a short circuit. Okay, so its spectral density was what? And what will be the output voltage spectral density? Yeah, it's this multiplied by square of the output resistance, which is GDSP plus GDSN. It's not related to, see, you have decoupled the noise. The noise is proportional to GM and the output impedance is proportional to 1 over GDSP. Okay, so the product will also be higher. Anyway, we didn't have to go through this. If you just look at the input referred spectral density, that's clear also, right? The input referred spectral density is the voltage spectral density. Okay, that is also higher in this case than if you use the passive load. Okay, this is simply because you have devices adding extra noise in the circuit. Yeah. Yeah. Yeah, that's correct. First of all, it is slightly different in that in this case the output current will be 16 by 3 kT GMN plus 16 by 3 kT times GMP. Okay. The output current will change to 8 times kT times, 4 times, yeah, it is 8 times kT times G. Okay. So from the output devices, first of all, you can't mirror, that is one problem. But besides that, so let's say it is of this form. So instead of GMP, you will have G. But you will need a much higher voltage, right, to do this. I mean, the reason we went to active load was because you cannot realize such a high impedance. Okay. So that is the bottom line here. So if you realize the same impedance with, actually, we went to active load because we can't realize an impedance equivalent to GDSP with a physical conductance. Okay. So now this GMP can be much more than G. Is okay? So this would be instead of GMP, GDSP, if we realize an equivalent conductance of GDSP using a physical resistor. Yeah. Yeah, that's correct. But, yeah, okay. What about it? No, I mean, it's not important, not enough to have just a large value of resistance. That will give you a small current, but what about signal? I think the assignment problems discuss these things, right? You are interested in the signal to noise ratio, okay, not in just the amount of noise. If you use high impedance circuit, what happens is you will have your signal current is also smaller. So the signal to noise ratio will still be bad, although the noise is poor. Okay, so the only time when you have a better deal with using a high resistance is when you have somehow an inherently current source. Okay, inherent current source. Normally we have voltage source. We have voltage sources and we convert it to current. So if you convert it to current using a high impedance, you will have a smaller signal current also. Maybe you have a smaller noise, but you also have a smaller signal current. Overall, you are worse off doing that. But if you have an inherent current source, like for instance the photodiode, you will have to make some of the impedances in the circuit very high. Okay, to get a high signal to noise ratio. Otherwise, if you are entirely in the voltage domain and operating from a voltage supply, voltage source supply, the best deal to get best signal to noise ratio is to lower all the impedances. Okay. If we had, all our batteries are voltage sources. Okay. If we had current source batteries, then you would do the other thing. You would make everything high impedance. Okay. So for most of our cases, I mean for every one of our cases, because we have voltage sources, we should lower the impedance to get high signal to noise ratio. Okay. Or if you try to minimize noise, in this case, you will get a low signal swing. Okay. So this, the first and second problem lead directly into the differential pairs frequency response and noise, which we'll discuss briefly tomorrow and moving on, right? The answers will be exactly the same. As you can see, so this was grounded in the quiz problem. Now it is connected to a current source, but it won't make much difference when you are looking at the current through this one. Okay.